The solutions of this system of n equations with n unknowns are called critical points for the function f. Third, as a result, after we solve the system, we have some solutions here. A, B, C, and so on, the critical points. Now, the next step is to compute the second order partial derivatives. And for each critical point, A, B, C, and so on, we compute the Hessian matrix. Usually denoted by H, HF applied to A, which contains the second order partial derivatives of the function f at the point A. This is a quadratic matrix, symmetric. Yes, it's a symmetric matrix. We know that the eigenvalues of a symmetric matrix are always real numbers. And now, by using the Hessian matrix, we can decide the nature of each critical point. So, first, if all eigenvalues of the Hessian matrix are strictly positive, A is a minimum, a local minimum. If all the eigenvalues of the Hessian matrix are strictly negative, then A is a maximum, a local maximum. And if there are both positive and negative eigenvalues, then A is not an extremum. If there are both positive eigenvalues and negative eigenvalues, then A is not a local extremum. Okay, this is the basic algorithm, and now let's apply this algorithm to decide the extrema of some particular functions. Let's consider, for example, the function of two variables, x at 4 plus y at 4 minus x squared minus y squared minus xy. Of course, the domain is the entire plane. So the question is to find the extrema, the local extrema. We follow the previous algorithm. We first compute the partial derivatives with respect to x and with respect to y. Now we need to solve the system which gives us the critical points. Now, usually we solve the system by substitution, but not necessarily. From the first equation, for example, y equals 2x minus 4x at 3, and we replace it in the second. So it's 4 times 2x minus 4x at 3 minus 2y minus 2x minus 4x at 3. Sorry. So we replace y by this value. So it's 4 times 2x minus 4x at 3 minus 2x minus y, which means minus 2x minus 4x at 3 equals 0. And we need to solve this equation. Which gives us here we take a common factor 2x. So it will be 2 at 3, it's 8. 32 x at 3 times 1 minus x at 3 minus 4x plus 4x at 3 equals 0. Which is 32x at 3 times 1 minus x at 3 minus 4x times 1 minus x squared equals 0. So we have 32x at 3 times 1 minus x times 1 plus x squared minus 4x times 1 minus x times 1 plus x equals 0. And we have a common factor 1 minus x times a parenthesis. And this gives us x equals 1 and so on. Maybe there are also other roots. When x equals 1, we get y equals minus 2. So we have, among other critical points, we have this critical point. And now we have to decide if this is an extremum. For that, we compute the second order partial derivatives. 12x squared minus 2. With respect to y, it's 12y squared minus 2. And the mixed second order partial derivative, it is minus 1. At the point 1 minus 2, here it's plus 2. Okay, so at the point 1, 2, we have the Hessian matrix will be minus 2, sorry. At the point 1 minus 2, we have the following. We have 10. Here we have 46 minus 1 minus 1. This is the Hessian matrix. Now the eigenvalues, we need to compute the characteristic polynomial. It will be 10 minus lambda minus 1 minus 1, 46 minus lambda, which gives us minus 1. And now the sign of the roots of this quadratic equation, which is lambda squared minus 56 lambda plus 459 equals 0. As we can see, both eigenvalues are positive, so the point, the given critical point is a local minimum. Okay, now let's try some other example. consider the function f of x and y equals still a function of two variables. X at 4 plus y at 4 minus 4xy. Again, we compute the partial. This time we shall make a complete computation. The first order partial derivatives are 4x at 3 minus 4y, 4y at 3 minus 4x. Now the critical points are given by the system. Written here. From the first equation, we get that y equals x at 3, and we replace it in the second. So we have x at 3 minus x equals 0. That means x times x at 8 minus 1 equals 0. This equation has three real solutions. X1 equals 0, x2 equals 1, and x3 equals negative 1. Correspond to these solutions, we have y1 equals 0, y2 equals 1, and y3 equals minus 1. So there are three critical points, 0, 0, 1, 1, and minus 1, minus 1. And now we shall decide the nature of each of these critical points. For that, we need to compute the second order partial derivatives, 12x squared with respect to y. It will be 12y squared, and the mixed second order partial derivative will be minus 4. So now the Hessian matrix in some arbitrary point, hf of xy, is 12x squared minus 4 minus 4, 12y squared. And now we shall consider each of these critical points to decide the nature. First, the Hessian matrix at 0, 0 is 0 minus 4 minus 4, 0. The characteristic polynomial will be lambda squared minus 16. So the roots lambda 1, lambda 2 are obviously 4 and minus 4. So there are positive and negative eigenvalues. That means 0, 0 is not an extremum, a local extremum. Now, what about the other two? The Hessian matrix at 1, 1 is 12 minus 4 minus 4, 12. The characteristic polynomial is given by this determinant, which is 12 minus lambda squared minus 16. That means 12 minus lambda minus 4 times 12 minus lambda plus 4, which means 8 minus lambda times 16 minus lambda. So both these eigenvalues are positive, so that means 1, 1. It's a local minimum. Similarly for minus 1, minus 1. Okay. Now, let's see a function, a rational function, for example, f of x and y equals xy plus 2 over x plus 5 over y. Here the domain of definition is without the straight lines x equals 0, y equals 0. Now we start to compute the partial derivatives. First with respect to x. Now the critical points. We have y equals 2 over x squared, and we replace it in the second equation. We get x minus 5 over 4 over x at 3, x at 4, sorry, equals 0. Which means x minus 5 over 4 x at 4 equals 0. X times 1 minus 5 over 4 x at 3 equals 0. So I have x1 equals 0, and x2, it's root of order 3 of 5 over 5, 4 over 5. When x1 equals 0, then y1 is 0 from here. And when x2 equals root of order 3, then y2 will be 2 over root of order 3 of 16 over 25, which means here we simplify by 2, and there will be root of order 3 of 25 over 2. And now we continue in the same way. These are the critical points. We need to compute the second order partial derivatives. Here we have to differentiate this with respect to s. This will give us 4 over x at 3. With respect to y will be 10 over y at 3. And the mixed second order partial derivative will be 1. So this will give us the Hessian matrix and so on. Now let's see something in 3 variables. For example, of a x, y, and z. 1 over x plus x over y plus y over z plus z. Here, of course, x, y, and z must be, all of them, different from 0. Okay, this is a function of 3 variables. The computation will be a little bit longer, but the algorithm will be the same. First, we compute the partial derivatives. And with respect to z, okay, now the critical points will be given by the following system. From the first equation, actually, we have y equals x squared. From the second equation, we have we replace y by x squared in each of the other 2 equations. So there will be minus x over x at 4 plus 1 over z equals 0. And the last one, minus x squared over z squared plus 1 equals 0. Now here, of course, we simplify by x. And from here we get that z must be x at 3. We replace z by x at 3 in the last equation, minus x squared over x at 6. Z squared means x at 6 plus 1 equals 0. So minus 1 over x at 4 plus 1 equals 0, which means x1 equals 1 and x2 equals minus 1. Okay, so consequently, when x is 1, y is 1, and z is 1. When x equals minus 1, y will be 1, and z2 will be minus 1. So there are two critical points, 1, 1, 1, and minus 1, 1, and minus 1. Okay, now we need to compute the second order partial derivatives. So with respect to x, with respect to y, the not mixed second order partial derivatives are given by these formulas. And now the second order mixed partial derivatives. The order of differentiation doesn't matter. This is 0. And with respect to y and z, they are minus 1 over z squared. Now the general in an arbitrary point Hessian matrix of f is given by it's a symmetric matrix, as we know from the theory. Sorry, here, no, here is 2y over z at 3. And here we replaced the wrong value. Here it's minus 1 over z squared, minus 1 over z squared. Okay. On the main diagonal, we need to have the not mixed second order partial derivatives. Yes. It's y at 3. And here is y. Okay. 0, 0. Okay. Now, we take the first critical point, 1, 1, 1, and we see the Hessian matrix at this point. It's 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. Now, the sign of the eigenvalues of this matrix will give us the nature of 1, 1, 1. The characteristic polynomial is this determinant. Actually, we don't need the exact values of the eigenvalues, but their sign. Well, in some particular cases, we can compute the eigenvalues. If not, their sign is enough. We compute the characteristic polynomial. So it is 2 minus lambda at 3 minus 2 times 2 minus lambda. We have the common factor 2 minus lambda times lambda squared minus 4 lambda plus 2, finally, plus 4 minus 2. So this is the characteristic polynomial. The eigenvalues are lambda 1 equals 2, and the other two are given by the quadratic equation lambda square minus 4 lambda plus 2 equals 0. As we can see, they are both positive. Lambda 2 and lambda 3 are both positive. We can compute them, but it's not important. So in this case, all the eigenvalues are strictly positive. Consequently, 1, 1, 1, it's a local minimum. Similarly, we decide the nature of the other critical point, -1, 1, and -1. I leave this as an exercise. Thank you.